Many physical entities, example, mass, energy, etc., are entirely defined by a numerical magnitude which is expressed in appropriate units. Such entities which have no directional element are known as scalars. Moreover, since scalars can be represented by real numbers, it follows that they obey the laws of ordinary algebra. However, there exists a second class of physical entities, for example, velocity, acceleration, force, etc., that are only completely defined when both a numerical magnitude and a direction in space are specified. Such entities are known as vectors. By definition, a vector obeys the same algebra as displacement in space and may thus be represented geometrically by a straight line with an arrowhead. The arrow indicates the direction of the displacement and magnitude of the vector is represented by the length of the straight line. In print, the vectors are conventionally denoted by bold-faced symbols and scalars by non-bold-faced symbols. The magnitude of a general vector A is denoted by modulus A or just A and is by definition always greater than or equal to 0. A zero vector is one that has zero magnitude and has no direction. Finally, two vectors A and B are said to be equal when their magnitudes and directions are both identical. We shall begin our discussion on vectors by learning four vector operations, addition, and three kinds of multiplication. Let's now discuss about vector addition. Suppose that we need to add two vectors, vector A and vector B. In order to add these two vectors, what we do is that we'll place the tail of B at the head of A, and the sum A plus B is the vector from the tail of vector A to the head of B. And vector addition is commutative. That means that vector A plus vector B is equal to vector B plus vector A. To bring home this point, let us consider this situation. So this is north, south, and this is east, and this is west. Consider the case of a person who is traveling from point P to point Q. He could first walk 4 meters towards east and then walk 5 meters towards north. So let us assume that this is vector P and this is vector Q. So the total displacement is vector P plus vector Q. This is equal to 4 plus 5 and this is equal to 9 meter. Let's now consider his movement along an alternate path. He walks a distance 5 meters towards the north first and then walks a distance 4 meters towards east. So this is vector Q and this is vector P, so that the displacement now is vector Q plus vector P. This is equal to 5 plus 4, this is equal to 9 meter. So this is what the commutative law of addition means. Vector A plus vector B is equal to vector B plus vector A. And the addition is also associative. That means vector A plus vector B plus C is equal to vector A plus vector B plus C. Let's now discuss about the subtraction vector A minus vector B. So this is vector A and this is vector B. To subtract vector B from vector A, what we do is that we'll reverse the direction of B. So this is the new direction of B and this vector is now indicated by minus B. To find the subtraction, what we do is that we'll add vector A and the negative of vector B. So that what we get is vector A minus vector B. Multiplication by a scalar. Multiplication of a vector by a positive scalar A multiplies the magnitude but leaves the direction unchanged. What you see here is vector A, and that is being multiplied by a scalar 2. Now you can see that the direction of the vector remains the same, but the magnitude has doubled. If A is negative, then the direction is reversed. So A was like this. If we multiply by minus 2, the direction of A will be like this. And scalar multiplication is distributive. That means a scalar A multiplied by vector A plus B is equal to scalar A multiplied by vector A plus scalar A multiplied by vector B. The dot product of two vectors. Let's consider two vectors, vector A and vector B, which are inclined at an angle theta. The dot product of the two vectors is defined by vector A dot vector B is equal to magnitude of vector A multiplied by magnitude of vector B multiplied by cos of angle between the two vectors, that is cos theta. But theta is the angle they form when they are placed tail to tail. The dot product vector A dot vector B is itself a scalar, and that is why it has an alternative name, the scalar product. The dot product is commutative. That means that vector A dot vector B is equal to vector B dot vector A. The dot product is distributive. That is vector A dot vector B plus vector C is equal to vector A dot vector B plus vector A dot vector C. Let's now try to understand the geometrical meaning of the dot product. We have two vectors, vector A and vector B, that are inclined at an angle theta. Now, the projection of vector B on vector A is B cos theta. So geometrically, vector A dot vector B is the product of A times the projection of B along A. We can also express this in another way. Let's write the dot product as vector A dot vector B is equal to modulus of vector A cos theta multiplied by the modulus of vector B. Now let us take the projection of vector A on vector B. So this is modulus of vector A cos theta. So alternatively, the dot product vector A dot vector B is the product of vector B times the projection of vector A along vector B. From the very definition of the dot product, we can conclude that if the two vectors are parallel, then vector A dot vector B is equal to modulus of vector A times modulus of vector B. In particular, for any vector A dot vector A is equal to A square. If vector A and vector B are perpendicular, then vector A dot vector B is equal to 0. Another kind of vector multiplication is the cross product. The cross product of two vectors is defined by vector A cross vector B is equal to modulus of vector A modulus of vector B times sin theta times n hat, where n hat is a unit vector, that is a vector having magnitude 1 pointing perpendicular to the plane of vector A and vector B. The direction of the unit vector n hat can be understood by the right hand rule, wherein if we consider the first vector as lying along the direction of the index finger and the second vector as lying along the direction of the middle finger, the direction along which the thumb will point will give the direction of the unit vector. Another technique to understand the direction of the unit vector n hat is the right hand screw rule. Let us assume that we have placed a screw at the intersection of the two vectors, vector A and vector B. Now, if you rotate the screw along the clockwise direction, that is from vector A to vector B, then you can see that this screw will actually go inward, so that the direction of n will be towards the inward of this screen. Now, if you rotate the screw in the anti-clockwise direction, that is from vector B to vector A, then you can see that the screw will actually move along a direction perpendicular to the plane of this screen. So the direction of the unit vector will be perpendicular to the plane of this screen. So this rule is known as the right hand screw rule. The vector cross product is distributive. That means that vector A cross vector B plus C is equal to vector A cross vector B plus vector A cross vector C. And vector cross product is not commutative because vector B cross vector A is not equal to vector A cross vector B. In fact, vector B cross vector A is equal to negative of vector A cross vector B. Let's now try to understand the geometric meaning of the cross product of two vectors. Let's consider two vectors, vector A and vector B, that are inclined at an angle theta. Geometrically, the magnitude of vector A cross vector B is the area of the parallelogram generated by vector A and vector B. From the very definition of the cross product, we can understand that if two vectors are parallel, their cross product is 0. In particular, the cross product of a vector by itself will be equal to 0. Here 0 is a 0 vector with magnitude 0. Let's now discuss the vector algebra in the component form. Let us assume that x hat, y hat and z hat be unit vectors parallel to the x, y and z axis respectively. An arbitrary vector A can be expanded in terms of the basis vectors ax times x hat, ay times y hat and az times z hat as vector A equal to ax times x hat plus ay times y hat plus az times z hat. So this term is the projection of vector A along the x direction, and this term is the projection of vector A along the y direction, and this term is the projection of vector A along the z direction. So this is ax times x hat, and this is ay times y hat, and this is the projection of vector A along the z direction. The numbers ax, ay and az are the components of vector A. Geometrically, ax, ay and az are the projections of vector A along the three coordinate axes, so that ax is equal to vector A dot x hat and ay is equal to vector A dot y hat and az is equal to vector A dot z hat. Let's now consider the different rules in vector algebra when we consider a vector in the component form. Rule 1. To add vectors, add like components. Let's assume that we have to add two vectors, vector A and vector B. So this is the component form of vector A and this is the component form of vector B. Now, if we combine the terms of x hat, y hat and z hat, we'll get ax plus bx times x hat plus ay plus by times y hat plus az plus bz times z hat. That means to add two vectors, add like components. We have added the components ax and bx and then ay and by and then az and bz. Rule 2. To multiply by a scalar, multiply each component. That means if you are going to multiply vector A by a scalar A, then the result is scalar A times AX times X hat, scalar A times AY times Y hat, scalar A times AZ times Z hat. Rule 3. To calculate the dot product, multiply like components and add. Before we discuss the dot product in component form, let's consider this. We know that x hat, y hat and z hat are mutually perpendicular unit vectors. Therefore, x hat dot x hat will be equal to y hat dot y hat, and that will be again equal to z hat dot z hat, which will be equal to 1. Similarly, x hat dot y hat will be equal to x hat dot z hat will be equal to y hat dot z hat will be equal to 0. Now, when we take the dot product in component form, vector A dot vector B is equal to the dot product of the corresponding components. When we take the dot product, we'll get the result AX BX plus AY BY plus AZ BZ. So that means that to calculate the dot product, multiply like components and then add. The dot product of a vector by itself will be equal to a square, that is ax square plus ay square plus az square, or the magnitude a will be equal to square root of ax square plus ay square plus az square. Rule 4. To calculate the cross product, form the determinant whose first row is x hat, y hat and z hat, and whose second row is vector A in component form and whose third row is vector B in component form. But before we calculate the cross product in component form, let's consider this. X hat cross x hat will be equal to y hat cross y hat, and that will again be equal to z hat cross z hat, and that will be equal to 0. And x hat cross y hat will be equal to minus of y hat cross x hat, which will be equal to z hat, and y hat cross z hat will be equal to minus of z hat cross y hat, and that will be equal to x hat, and z hat cross x hat will be equal to minus of x hat cross z hat, which will be equal to y hat. Now, using these identities, we can show that vector A cross vector B is the cross product of the corresponding components, and then when we expand, we have ay bz minus az by times x hat plus az bx minus ax by times y hat plus ax by minus ay bx times z hat. And this cumbersome expression can be written more neatly as a determinant as vector A cross vector B equal to determinant x hat y hat z hat ax ay az and bx by bz. So that to calculate the cross product, form the determinant whose first row is x hat y hat z hat, whose second row is A in component form, and whose third row is vector B in component form. Let's now try to solve this problem. Find the phase angle between the phase diagonals of a cube with unit side lengths. In this figure, we have placed the coordinate system at one of the corners of the cube, and we consider two phase diagonals represented by vector A and vector B. So what we are considering is this phase and this phase. Since the cube has unit side lengths, this point is 1 0 0 and this point is 0 1 0 and this point is 0 0 1. Now the coordinate of the head end of vector A is 1 0 1. The coordinate of the head end of vector B is 0 1 1. Now the origin is 0 0 0. Now we want to find out vector A and vector B. The general expression for vector A is A equal to x2 minus x1 x cap plus y2 minus y1 y cap plus z2 minus z1 z cap. So this is equal to 1 minus 0 x hat plus 0 minus 0 y hat plus 1 minus 0 z hat. So this is x hat plus 0 y hat plus z hat. So this is x hat plus z hat. Now B is equal to 0 minus 0 x hat plus 1 minus 0 y hat plus 1 minus 0 z hat. So this is x hat plus y hat plus 0 times x hat plus y hat plus z hat. So this is equal to y hat plus z hat. Now let's find out A dot B. Vector A dot vector B is equal to x hat plus z hat dot y hat plus z hat. So this is equal to x hat dot y hat plus x hat dot z hat plus z hat dot y hat plus z hat dot z hat. Since x and y are mutually perpendicular, this dot product is 0 and this dot product is 0 and this dot product is 0 and this is equal to 1. So A dot B is unity. Now we also know that A dot B is equal to modulus of vector A modulus of vector B times cos theta. This we have found out to be 1. Now modulus of vector A is equal to square root of 1 square plus 0 square plus 1 square. So that is equal to square root of 2, and modulus of vector B is equal to square root of 0 square plus 1 square plus 1 square. So that is equal to square root of 2. That is square root of 2 times square root of 2 cos theta is equal to 1. So that is 2 cos theta is equal to 1, or cos theta is equal to 1 by square root of 2, and theta is equal to cos inverse 1 by square root of 2, which is 60 degree. The next problem is to find the angle between the body diagonals of a cube with unit side lengths. Like in the previous case, we have placed the coordinate system at one of the corners of the cube, and we have considered two diagonals represented by vector B starting from the origin and ending at this point, and we are also considering another body diagonal starting from here and ending at here. Now this point, that is this coordinate, is represented by 1 0 0, and this coordinate is represented by 0 1 0, and this coordinate is 0 0 1. Now we shall write the coordinates of the head end of vector A. This is 1 1 0. For the head end of vector B, this will be 1 1 1. And now we shall try to write vector A, which is vector A equal to 1 minus 0 x cap plus 1 minus 0 x hat plus 1 minus 0 y hat plus 0 minus 1 z hat. So this is equal to 1 x hat plus 1 y hat minus 1 z hat, and modulus of vector A is equal to square root of 1 square plus 1 square plus 1 square equal to square root of 3. Similarly, vector B is 1 minus 0 x hat plus 1 minus 0 y hat plus 1 minus 0 z hat. This is x hat plus y hat plus z hat, and modulus of B is equal to square root of 1 square plus 1 square plus 1 square. So this is equal to square root of 3. And we know that vector A dot vector B is equal to AB cos theta which is equal to 1 dot 1 plus 1 dot 1 minus 1 dot 1. So this is equal to 1. Now magnitude of vector A is square root of 3 and that of B is square root of 3 times cos theta is equal to 1, or cos theta is equal to 1 by 3 and theta equal to cos inverse 1 by 3, which is 70.5288 degrees. So the angle between the body diagonals of a cube with unit side lengths, that is angle theta, is 70.5288 degrees. The vector triple product. The cross product of two vectors is itself a vector. Now, this can be dotted or crossed with a third vector to form what is known as a triple product. A triple product is defined as vector A dot vector B cross C is equal to vector B dot vector C cross A, that will again be equal to vector C dot vector A cross vector B. Note that an alphabetical order is preserved in the case of scalar triple product. That means that we have A dot B cross C or B dot C cross A and then C dot A cross B. In component form, the scalar triple product vector A dot vector B cross vector C is equal to determinant Ax, Ay, Az, Bx, By, Bz and Cx, Cy, Cz. Note that the dot and cross can be interchanged. That is, vector A dot vector B cross vector C is equal to vector A cross vector B dot vector C. However, the placement of the parenthesis is critical because the term in the parenthesis is a scalar and we cannot take a cross product of a scalar and a vector. Let's now try to understand the geometrical meaning of scalar triple product. Let's assume that vector A, vector B and vector C lie along the three sides of a parallel pipette. Now, the area of the base is nothing but the magnitude of the cross product vector B cross vector C. So this is the area of the base. Now the altitude is nothing but magnitude of vector A times cos theta. Now the volume of the parallel pipette is base area times altitude. Therefore, we have modulus of A cos theta dot modulus of B cross C. which is equal to modulus of A dot B cross C. Now we will discuss about the vector triple product. A vector triple product is defined as vector A cross vector B cross vector C. The vector triple product can be simplified by the BAC-CAB rule. That is, vector A cross vector B cross vector C is equal to vector B times vector A dot vector C minus vector C times vector A dot vector B. Notice that vector C cross vector A cross B is not equal to vector A cross vector B cross C. In fact, vector C cross vector A cross B is the negative of vector A cross vector B cross C. So this can be proved from the BAC-CAB rule. Let's begin with vector C cross vector A cross vector B. So when we expand this using the BAC-CAB rule, this will be vector C times A dot B minus vector B times A dot C. So this is negative of vector B times vector A dot vector C minus vector C times vector A dot vector B. This is nothing but negative of vector A cross vector B cross vector C. In electrodynamics, we will often come across the position, displacement and separation vectors. We are going to have a discussion on these vectors. The position vector. Let's consider a point here. We'll assume a Cartesian coordinate system x, y, z with origin O. The location of the point can then be described by listing its Cartesian coordinates x, y and z. Now you can see from this figure that this point is at a distance vector r from the origin, and r hat is a unit vector along the direction of vector r. The vector to this point x, y, z from the origin O is called the position vector. We will denote the position vector as vector r equal to x, x hat plus y, y hat plus z, z hat. The position vector r, which is expressed as x, x hat, y, y hat and z, z hat, can also be written as modulus of vector r times the unit vector along the direction of vector r. So that is modulus of vector r times r hat. So this is equal to r times r hat. Now the magnitude of vector r is the distance from the origin, which could be calculated to be r equal to square root of x square plus y square plus z square. Now the unit vector pointing radially outward can be written as r hat equal to vector r divided by r, that is equal to x, x hat plus y, y hat plus z, z hat divided by x square plus y square plus z square. The displacement vector. Let's now consider 2 points x, y, z and x plus dx, y plus dy and z plus dz. Let's assume that these 2 points are separated by a distance vector dl, so that we can write vector dl as equal to dx x hat plus dy y hat plus dz z hat, and this vector is known as the displacement vector. The separation vector. In electrodynamics, one frequently encounters problems involving 2 points. Typically a source point where an electric charge is located and a field point at which we will be calculating the electric or magnetic field. If we consider an origin O, then the source point is at a distance vector r prime and the field point is at a distance vector r. The separation between the source point and the field point is represented by vector script r. Vector r script is the resultant of vector r prime and vector r. To show that, let's redraw this picture. If you want to add two vectors, then the head of one of the vectors will have to be at the tail of the second vector. So this is O and this is vector r prime and this is vector r. So that this will be the resultant of the two vectors. Now this is plus r prime, therefore this will be negative r prime, so that the resultant will be vector r minus vector r prime. That is, script r is equal to vector r minus vector r prime. Its magnitude is given by script r is equal to modulus of vector r minus vector r prime. A unit vector in the direction from vector r prime to r is given by script r hat is equal to vector script r divided by script r, that is equal to vector r minus vector r dash divided by modulus vector r minus vector r dash. In Cartesian coordinates, vector script r is equal to x minus x prime times x hat plus y minus y prime times y hat plus z minus z prime times z hat. And the magnitude of r script is square root of x minus x prime the whole square plus y minus y prime the whole square plus z minus z prime the whole square. Now vector script r is equal to script r times script r hat, from where we can write the unit vector script r hat is equal to x minus x prime times x hat y minus y prime times y hat plus z minus z prime times z hat divided by square root of x minus x prime the whole square plus y minus y prime the whole square plus z minus z prime the whole square. Let's now try this problem. Find the separation vector script vector r from the source point 287 to the field point 468. Determine its magnitude and construct the unit vector. So the coordinates of the source point is given to be 2, 8 and 7, and that of the field point is given to be 4, 6, 8. Let's now try to construct vector script r, which is 4 minus 2 x hat plus 6 minus 8 y hat plus 8 minus 7 z hat. So this is 2 times x hat minus 2 times y hat plus z hat. Now when we find out the magnitude of vector a, this will be square root of 2 square plus 2 square plus 1 square. So this is equal to square root of 4 plus 4 plus 1 square root of 9, that is equal to 3. Construct the unit vector script r hat. So that is script r hat is vector script r divided by modulus of vector script r. So this is 2x hat minus 2y hat plus z hat divided by 3. So this is 2 by 3 x hat minus 2 by 3 y hat plus 1 by 3 z hat.